Hello everyone and welcome back. Today we're going to continue our investigation of some optimization methods, in particular related to graphs and network optimization. Before we get into the main example of this discussion, I just want to briefly mention a few concepts from graph theory that you may or may not already be familiar with. So first off, what is a graph? So a graph is an ordered pair VE, where V stands for the set of vertices or nodes, and E is just a set of edges. So if I just draw a very simple graph, for example, we can consider these three vertices. Some people again call them nodes, and let's assume that we name this A, B, and C. So if I just say that this is my graph G, then my vertices consist of A, B, and C. So V is a set of locations, I guess you could say. And now I'm going to connect these points in a way. For example, I can connect A with B, B with C, and A with C. That means my set of edges, E, consists of AB, AC, and BC. So I have three vertices, three edges, and the pair of these two sets is my graph G. Okay, now notice that I do not have any directions here. For example, I can go from A to B, or I could go from B to A. I'm not sort of restricting a one-way direction here. Same thing for B to C, and C to B, and A to C, and C to A. So I just want to mention one quick thing here. So these are what we call undirected edges. So for undirected edges, this statement AB is equivalent to BA, right? So going from A to B and B to A corresponds to the same exact edge. Now I can impose a one-way direction. For example, I can say again the same exact vertices. Let's call them again A, B, and C. Let's draw these edges. But now what I'm going to do is I'm going to mandate a particular direction. So I'm going to mandate A goes to B goes to C, and C goes to A, but not the other way around. So if you want to go from B to A, you have to first go to C and then go to A. You cannot go from B to A directly. So this is what we refer to as a directed graph. And there's a few ways to represent this in the graph theoretical context. For example, we can say V, again, is the set of vertices A, B, and C. And then my set of edges E is going to be A to B, but I'm going to do a direction there. So A to B with a direction, and then B to C with a direction, and then C to A with a direction. Right? So B to A, C to B, and A to C are not edges in this particular graph, and again, some people will call these directed edges. Right? So this is just a couple basics. So from these basic definitions, you should be able to come up with the following observations, in particular for a directed edge, AB is not necessarily equal to BA. And another important observation, if AB is undirected, then AB and BA represent the same exact edge. So in terms of graph notation, if I show these two vertices, where you could either go from A to B or B to A, then this is equivalent to just writing the notation A to B. So if you allow A to go to B and also B to go to A, instead of writing these directed notations, you can just write A, B. Right? So this is just some basics of graph theory that you should be aware of. And there's one more definition that I want to introduce. There are several other graph theoretical concepts that one would explore in graph theory, but I just want to define this last one. So a graph G with vertices V and edges E is said to be connected if there exists an edge in G between every pair of vertices. or not necessarily an edge, but more so a sequence of edges in G. Between a sequence of edges in G between every pair of vertices in V. So what exactly do I mean by that? So let's assume I have this particular graph, A, B, C, and then D. And let's assume that this is a directed graph, in particular that way. Is this graph a connected graph? Right? So A is connected to B, B is connected to C, and C is connected to D. But if I want to connect A and D, I cannot do so, right? So in this graph, this is not a connected graph, but if I sort of remove those directions, then it would be a directed graph because I could just go from D to C, C to B, and B to A, right? So there's just some basic concepts associated to graph theory that we're going to be using for this main concept, which is associated to linear programming. So now let us introduce the main problem that we want to solve via graph theory and linear programming, which is sometimes referred to as the minimum cost flow problem, and you can also reverse this to be a maximum flow problem as well. So what we're going to do is we're going to begin by defining xij to be the amount of product that is going to be delivered from location I to location j, and let's assume that cij is the cost of that particular shipment or delivery from I to j. It's very important that xij is not necessarily equal to xji, because if you deliver it from A to B, and you also deliver it from B to A, then in a sense, what's the point of delivering it at all? Because that probably won't minimize anything because you've just wasted that entire trip because, it nets out to zero. So what our goal is to deliver, for example, all of the products to all of the stores and minimize this cost Cij throughout all of the possible delivery routes. So let's actually write that down in matrix form. So our goal is to minimize our functional f of x, and this is going to be equal to the sum across all ij, and this is going to belong to our edge set of cij times xij, right? So that's, of course, the product of cij and xij. For example, the cost of route 1 and the cost of route 2 and the cost of route 3, and the sum of all, so this is pretty much a total cost function. And it's Cij and Xij. It's not Xi or Xj because the two directions possibly will exist, right? Because some other trucks may go in the opposite direction, but some trucks will go in the forward direction. And of course, we can write this in matrix notation as C transpose X. So C is going to consist of all our Cijs, and X is going to consist of all of our Xijs across all of the edge routes in our particular map or graph, you could say. So the sum is across all directed edges. All right. Now let's define the vertices in our particular graphs. So vertices will have three forms. So the first form that they could be is a supply vertex. The third, or the second, is going to be a demand vertex. And then a third is going to be what we refer to as a transfer vertex. So a supply vertex is going to have a supply, and let's call the supply, let's call it, say, BI, and let's assume that it's greater than 0. So for example, I have 5 loaves of bread that I plan to deliver amongst, for example, at most 5 stores, right? So if you don't have a positive supply, then it's not a supply vertex because it can't really give things to stores, right? So of course it's going to start off at BI is greater than 0, but it should converge closer to 0, provided that the supply vertex is not isolated from the graph, i.e. this graph is, of course, connected. And then we're going to have our demand vector, so we're going to call the demand of that also BI, keep in mind I is going to range from 1 to, the number of vertices. So some vertices are supplies, so they're going to have positive coefficients associated to them. And demand vectors are going to start off at negative because they need things. So it's going to, of course, start off at 0 or start off negative, and it's going to converge closer to 0. Just, from the other direction. You don't want it to converge to a positive number because then you're going to have a surplus, right? So for example, if I have 5 loaves of bread and all of my stores cumulatively want 5 loaves, then of course my supply is going to depreciate to 0, and the demand also is going to increase to 0 because they have all of the things that they need. And then we have our transfer vertex, which is no supply and also no demand. So it's pretty much just a location in our graph where trucks are sort of going to pass through, or they sort of have to pass through. They're not going to drop anything off, and they're not going to pick anything up there. So no supply and no demand. So therefore we're going to let BI to be equal to 0, and that should stay relatively fixed or balanced throughout the entire process for our particular networked optimization problem. Now let's state a couple requirements that we have. So some restraints. So some requirements and constraints for our linear program. So we're going to let Lij to be the minimum. So it's the lower bound amount of product that is allowed to be delivered along, let's see, that path, let's call that path, say, Eij, the path from, say, Vi to Vj, and Uij to be an upper bound on the amount of product that can be delivered along Eij. So if no restrictions exist, we're going to default to the following. In particular, we're going to let Lu be equal to 0 to positive infinity for every single one of the routes, right? So you're not going to have an upper bound for the amount that can travel along some particular bridge or some route or between two mountains or something like that. So that is what we're going to default to. And let's assume we don't have any restrictions on the minimum that has to pass through that particular route. So now let us formulate the linear program structure that we seek to optimize. So of course our objective function is to minimize this functional ij along the set of edges of Cij xij, so the cost times the amount along that route. So again, that's going to be ctx in vector form. And then subject to, now this might not be obvious, but let's just sort of think about that. So we're going to sum across all j such that ij is in E for xij, and then minus the sum across all I of ji in E. So notice here in the index, notice that that's ij and that's ji, so it's in the opposite direction. And notice that that is going to be equal to, so again that's xij, and we want that to be equal to bi, where I is equal to 1, 2, down to the number of vertices we have. So maybe take a moment to pause this video and sort of think about what this represents. But you can view this, for example, you can view this first summation as the flow out of a vertex minus the flow in. Flow in to a vertex. Okay? So, for example, if we think about the transfer nodes, right, we know that the BI should be equal to 0. So the flow in minus the flow out should balance out to 0 because the flow in and the flow out should be equal to each other. If we think about this from the supply node, remember the supply node BI is a positive number. So the flow out minus the flow in, you shouldn't have anything flowing into a supply node because the supply node has no demand. Therefore, the flow out should dominate the flow in, leaving us with a positive number for supply, and similar can be interpreted for the demand nodes as well, because the demand node has BI to be negative, and therefore the flow into that should be dominating the flow out of that particular vertex. So that's why we're creating this to be our constraint for our linear program. And of course, our constraints is that Lij must be less than or equal to Xij is less than or equal to Uij, which is going to be defaulted to Xij is greater than or equal to 0 if no other restrictions are imposed onto this. So if we write this in standard form, which is going to be very, very useful for solving things both on hand and in computers, what we're going to do is we're going to minimize this functional f of x, which is going to be equal to ctx, subject to the constraints ax is equal to b, such that x is greater than or equal to 0. So even if those constraints and restrictions are not in standard form, we already discussed how to convert every linear program into standard form just in case we need to. Also, you should be able to show, so one can show, or actually one can let. It's not a requirement. So one can also let the sum, all of our BKs, to be equal to 0, theoretically. For example, there's not going to be any shortages and there's not going to be any surpluses across all of our things. So nobody's going to be losing money across the entire scheme. Of course, this is not practical for the real world scenario, but we're actually going to be letting the sum of our BKs be equal to 0. So for example, if somebody demands 5 loaves of bread, I'm not going to have 6 loaves of bread in stock. I'm only going to have exactly 5, not less or more. So that's going to be our setup. Now let us get into a particular application of this and see if we can code this up into a linear program. So let's begin designing our network that we seek to optimize. Let's start off with a demand node up here. So let's assume that's going to be a store. And let's throw another demand node on the other side of the city. Let's call that D2 for our second demand node. So we're only going to have 2 stores and we're going to put a bunch of little suppliers across the different cities. So for example, where do I want the next node to be? So let's put the supply node there. Let's put another supply node here. Let's put another supply node here. Let's put another very convenient for one supply node there. And then let's do a transfer node there. Okay, so a bunch of supplies, a bunch of demands, and just one little transfer node sort of in the middle. So in terms of the directions of this particular graph, let's assume that S4 can deliver to D1 directly. Let's assume S6 can deliver to D1 directly. Let's assume that S3 cannot get to D1 or D2 and it has to sort of go through this transfer node. But once it gets to this transfer node T7, it can go to D2 if it wants to, but it cannot go to D1, at least in this example. Let's assume that S5 can go to D2 directly. S5 can go to T7 directly if it wants to. Possibly that route is a little bit more cheaper. And also let's make this connected. Let's assume that S6 can deliver to D2 as well. Let's also assume, let's make this fun. Let's assume that S4 can deliver to D2 as well. And let's assume that S5 can deliver to D1 as well. Okay, let's assume that those paths do not cross. So let's assume that that is our particular graph. Now that we have our graph, now let's state our demands and our supplies. So let's assume that D1, or our first node, requires 25 units. And let's assume we only have 1 unit. If you have multiple units, it's a little bit more difficult to code. And let's assume that D2 requires -30. So we're going to be letting all of our supplies and demands be equal to B sub k, where k is the index of our node. These, of course, numberings are not unique. As long as you stay consistent, that's all that matters. So, of course, B7 is going to be equal to 0 because that's a transfer node. Let's assume that 3 has 10 to supply. Let's assume that 6 has 20 to supply. Let's assume that 4 has 15 to supply. And let's assume that 5, so how much should 5 have to supply if there's no surplus or shortage? So notice that there's a total demand of negative 55, and right now we have 20 plus 10 is 30, plus 15 is 45, so if we want a total of 55, then B5 has to be equal to 10 to sort of make everything in equilibrium. So that is going to be a graph, and how many vertices do we have? So we have 7 vertices, and you can also figure out how many edges you have. You should be able to find that we have 9 edges in this particular graph. So now let us state, and you should be able to save this picture because that's what I'm going to reference for the rest of this solution. So now what I'm going to do is I'm going to define my x vector, and some people will call this our flow vector. So this is going to map out all of my edges. So for example, we can go from 4, 1, we can go from 5, 1, we can go to 6, 1, we can go to 4, 7, we can go to 6, 7, and then we have 5, 7, 3, 7, 7, 2, and then 5, 2. Now, of course, this is how many edges, so this should be a 9 by 1 vector, where a 9 is the number of edges. So let's just sort of recollect what we're doing here. So for example, we have 6 to 1, we have 5 to 1, we have 4 to 1, 4 to 7, 3 to 7, 5 to 7, 5 to 2, and 7 to 2, and finally 6 to 7. And let's assume that we want to go in this order. Again, it doesn't matter the order as long as you stay consistent. All right, so those are all of my flows. And now let's define our B vector. So this is going to be our supply and demand vector. So, and this is based on your numbering of your vertices. So this is going to be minus 25, minus 30, 10, 15, 10, 20, and 0. And this is going to be a 7 by 1 vector, where this is the number of vertices. And again, this is called our supply and demand vector. And it should only be 0 if it's a transfer vector. And lastly is going to be our cost vector. So C is going to be our cost vector. So our cost is going to be across each of the edges. So we're going to have C41, C51, C61, C47, C67, C57, C37, C72, and C52. Right? And keep in mind, these have to be in the same order as x. But again, this is a 9 by 1 vector, and of course this 9 corresponds to the number of edges. And let's just define our cost for each of these routes. Let's assume, for example, this is $5, $8, $4, $6. Let's have these matched up. For example, along 4, 1, that's going to be equal to 5, 8, 4, 6, 3, 4, 2, 3, and 10. So what is 10? So C, 10 is associated to path 5, 2. So where is 5, 2 located? So 5, 2 is this route here. So according to our cost vector, that's the most expensive route in this particular picture based on my cost vector C. All right. So now that we have defined our flow vectors, our supply and demand vectors, and our cost vector, now we need to define our coefficient matrix A for our linear program. So I've gone ahead and outlined what the coefficient matrices structure is going to look like. So along the rows, we're going to have our vertices, and our columns are going to be associated to the number of edges, because the edges correspond to the cost across those particular paths or directions, which is also located to how many units we need to deliver across each of those paths, which is going to be our unknown variable x1, x2 down to, for example, be x9, or x41, x51, x61, all the way down to x52 as we defined them before. So it's very important that you keep consistent with your indices for your vertices and the order for which you've defined your edges. You'll get the same answer, but the original matrix may be a little permuted if you want to use a different order. But keep in mind that this is going to be a 7 by 9 matrix, where 7 is going to be the number of vertices and 9 is going to be the number of edges in your particular graph. So in this particular matrix, you should only have either 1 or -1 inside this matrix. So let's just review whether it's going to be 1 or -1. And where are they coming from? That's coming from the flow in, flow out principle that we defined before. So +1 is going to be corresponding to flow out on the edge, and then -1 is going to be corresponding to flow in on an edge, right? So if you look at, for example, vertex 1, let's just take a look at our graph here. Let's look at vertex 1 just a bit. So keep in mind, +1 flow out, -1 flow in. So if we look at our picture for node 1, so node 1 is located right here, notice that we have 3 flows into it. We have a flow from 4, we have a flow from 5, and we have a flow from 6. In particular, we have a flow along 4, 1, 5, 1, and 6, 1. So 4, 1, 5, 1, 6, 1, which are going to be the first 3 columns, are going to be our flow ends. And since they're flow ends, those are going to be -1. So we're going to have -1, -1, -1, and there's not any flows from any other vertex into vertex 1, therefore these are all going to be zeros. Now what about vertex 2? So vertex 2 is located, where is vertex 2? Vertex 2 is located over here. So we have flows from vertex 5 and vertex 7. Those are the only 2 flows, and they're both flow ends. So we have 5, 2, and 7, 2. So 5, 2, and 7, 2, those are going to be our last 2 columns. Those are both going to be -1s, and then these are going to be zeros as well, since there's no flows from those particular vertices. So let's look at, for example, vertex 3, and then you can figure out the rest of this matrix. So vertex 3 is located here. So notice that this is a flow out. In particular, it's a flow out along path 3, 7. So 3, 7 is going to be located here, and there's no other flows, so the rest of these columns are going to be 0. And you should be able to complete the rest of this matrix to be the following: 1, 0, 0, 1. And you may pause the video now if you want to try to do this on your own. Row 5 is going to be 0, 1, 0, 0, 0, 1, 0, 0, 1. And then we have 0, 0, 1, 0, 1, 0, 0, 0, 0, and then lastly 0, 0, 0, -1, -1, -1, -1, 1, and 0. So why is this last row so complicated? So remember vertex 7, we have some flow ins, so flow ins from 3, 6, 4, and 5, and a flow out along 2, right? So 1, 2, 3, 4 flow ins and 1 flow out. So 4 negatives and 1 positive, and that is your coefficient matrix A. Now, once you have your matrix system A, and we also have our functional f of x, for example, we're seeking to minimize our cost flow function CTX, subject to that matrix AX is equal to B, where B is those supply and demand vectors, and also we're assuming that X is greater than or equal to 0. That is the minimum value we can have as 0, and we have no upper bound on those values. So you could either use, for example, computer software, because this is definitely a large matrix to work with, and if you're familiar with any of the linear programming methods, which we'll definitely get to, then you can perform them on this as well. So one can find, once you are aware of how to solve these things, the optimal solution to this problem is going to be the following. So x is going to be equal to, and keep in mind we're going to have an optimal value along each of those paths. So 4, 1, 5, 1, 6, 1, 4, 7, 6, 7, 5, 7, 3, 7, 7, 2, and 5, 2. So that's my 1, 2, 3, 4, 5, 6, 7, 8, 9 different paths and the amount for which I need to distribute along each of those paths. So one can find the optimal solution that minimizes the cost is going to be 15, 0, 10, 0, 10, 10, 10, 30, and 0. Right? Now there's a couple interesting things to think about here. For example, what do these zeros mean? So if I want to minimize the cost for these deliveries across all these stores, I would deliver absolutely nothing along Route 51, 47, and 52. So technically, if you're thinking about this from an economic standpoint, you can eliminate these edges. So edges can be eliminated, right, for at least this particular problem. So if you look at the eliminated routes, we're just going to be left with S4 to D1, S6 to D1, S6 to our transfer node, S3 to T7, S5 to T7, and T7 to D2. Right? So what routes did we remove here? So we removed that one because I guess it was too long. We removed that one because I guess it's too long. And we removed that one because I guess it went through the mountains or the rivers or had to go underwater or some crazy stuff like that, right? So we eliminated those routes. So this is the only route that's going to have deliveries across all of it. Okay, so let's take a look at what's actually going on here. For example, if we look at route 4.1, and 6.1. So 4.1 and 6.1, the amount we need to deliver along it is 15 and 10. So 4.1 is located here, and 6.1 is going to be located there. So we need to deliver 15 along 4.1 and 10 along 6.1. And remember, we had a demand of minus 25. So notice that those are actually going to be met. So in particular, x41 plus x61 is going to be equal to 25, which was equal to the demand that they had for node D1. Okay, so if we look at, for example, 6.7, 6.7 is going to have 10 located to it. 5.7 is going to have 10 located to it. And we have 3.7, which is also going to have 10 to it, and 7.2 is going to have 30. So if we look at those particular things, for example, x6.7 plus x3.7 plus x5.7, those are all going to be equal to x7.2, right? So that's going to be our flow ins and then our flow outs. Because remember, the supply and demand for T7 is going to be equal to 0 because of the transfer node. Okay, so those, the ins and the outs, are in balance. And remember that the old demand for D2 was going to be 30, and notice it's getting 10 from S6, 10 from S3, and 10 from S5, because obviously there's nowhere else that those supplies can go, so everybody is satisfied in terms of the supply and demand perspective. So that's how you can use linear programs and graph theory to optimize networks from either a minimum cost flow perspective or even a maximum cost flow perspective, just looking at the opposite objective function. I hope you enjoyed, and I'll see you in the next video. Take care.